All right, we're
All right.
recording.
All right. So hello, everybody. My name is Laura Harlow, and I am with the Teach Houston program. So I can be higher.
Yes,
I'm with the Teach Houston program, and I am one of the professors in the Teach Houston program. Our program is a capstone for NSM majors, and we are the teaching element for STEM majors. So we certify for secondary math, science, and now we're bringing in computer science as well. So I was a high school math teacher for 22 years. I loved it. I loved it. I loved it. I was never going to be a teacher, and I happened into it, and I said, well, this is what I'm supposed to do. So I am bringing in the computer science. I'm trying to bring in the computer science element, though, because as you know, as well as I do, we need people that are passionate and understand the material in the high schools teaching the material to help foster that passion about it. So, and this is Stephanie, and I'll let her talk.
Okay, so my name is Stephanie Huffman. I'm a biology major, and I'm in the Teach Houston program. So I was in a classroom kind of like you are and heard about scholarships, and I was like, money, free money, okay. I'm not a millionaire. I'll take it. And just kind of thought, you know, teaching, my mom always told me I should be a teacher, so I'll go ahead and just try it out. And I absolutely loved it. If you want to try it out, the first semester is actually you go into the elementary classroom, and they give you all the lesson plans, so you don't actually have to write any lesson plans yourself. You meet once a week, and it's a really easy course and just super fun. See if you like it or not. After taking the first course, you're actually allowed to apply for scholarships, so 80% of the students in the program are on scholarship. They also offered paid internships, which are really fun. You get to teach during the summer to students. We did one this past summer, and it was on the engineering design cycle. So we had these students that applied to be on it, to be a part of it, and what they did is they came in and they actually created their own invention. And we taught them about 3D printing and all this fun stuff and computer programming, and then they got to actually make their own prototype and pitch it to some of the people from the Inventors Association of Houston. So we had winners that are actually going on in a couple of months to the Young Inventors big competition. But so there's a lot of different things involved in the process, just like she said, that your capstone is fulfilled, which is a great way. You get life skills as well. And so if you decide that you don't want to teach in the end, at least you have all these really good skills to go along with it that you've learned, and it's been fun. And but if you do want to go into teaching, the starting salary for teachers, anybody know what it is? Any ideas?
$8.
For a 9-month contract. What, anybody know? $53,000. Starting is about $53,000. You do get, because you're actually degreed in science or math, you do get a little bit more of it, or computer science. Yeah, you do get a little bit more of like a bonus, is like $2,000-3,000.
A sign-on bonus sometimes, yeah.
So
depends on the district.
Yeah, so you're looking like 55, 56 starting pay right out of high school. You don't, right out of college. You don't have to live in mom and dad's house anymore and all that stuff, you know. So hey, it's a good option. And
so a couple of things I did want to say. Let me come back. So a couple of things I did want to say about. I know this is a 4,000 level course, and so as such, I'll try to get higher. As such, I'm just afraid I can't see over. As such, we do have a post-bac certification program that's going to start in the fall. Who in here is graduating this semester? Nobody graduating? Is somebody graduating this semester?
Yeah, there's
a few. Okay,
quite a few.
so we are a few, maybe online as well.
Yeah.
So what we're having, we do have a post-bac program right now, and it is for the cohort that begins in the fall 2019. You would take your courses for the Teach Houston program in the fall, and then you would take your student teaching in the spring, and right now is 100% scholarship. So it is for the 2 semesters, you get all your tuition paid for. It's completely scholarship, and then you would be, at the end of that time, you would be certified to teach. At this time, I will be completely honest with you, at this time, we do not have a pathway for a computer science certification. So let me explain to you how that would work. Because computer science majors have so much mathematics in your degree plans, you would end up being certified under mathematics, and you have the math for it, believe me. And so then what you would do is once you finish that certification, I think you have to wait 3 months, you turn around, and then you do your certification for computer science. What, in state of Texas, once you're certified in one content area in secondary, which is what we certify, then you can turn around and you can take another content area and be certified for that as well. So we're working on the degree plan for the certification in computer science. It's just not there yet. So for this plan, you would do your math and then turn around and do the computer science. Okay.
And secondary is 7 through 12, so you'll be
Grade 7 through
certified
12.
in 7 through 12.
Yeah, and we do have some, it's not, right now math is the only requirement for teaching computer science. It's not required that you're computer science certified. It's required that you are math, you can be math certified. But like I said, you know, the passionate teachers come from the people that are passionate about the content. And that's what gets us. That's what gets us there where we want to be inspiring the students. So, did y'all have any questions? Oh, we have an information session. Of course, I forgot that that flyer. So,
woman after my own heart.
I thought it was in the thing that they had packed for me, but it's not. And so we do have an information session. I probably will bring some by maybe next week or on Wednesday.
I'm remote on Wednesday only, so if
Got
you want to send it to me,
I will do that, and I'll send it out. Okay. And so we do have an information session next Wednesday, the 10th. On the 10th of April, on the 10th of April, we have an information session specifically for computer science majors, okay? It is in PGH, it is in PGH, and it's from 10 to 11, and I will send that out, and we'll get that out to y'all, and that is, I'm going to be there. What specific questions do you have about computer science, the way it works? One thing I've said, I've got one more minute. Mm-hmm. One thing I talked to some computer science majors, and they said that people had been in our program and they're like, there's nothing for computer science majors, really? I've been working on it. I promise you I've been working on it. And right now in our second course, all of our computer science majors that wanted to be with a computer science teacher are there. So they're teaching computer science classes in a middle school right now. And then we're going to move in, we're going to follow them into the high school. And when they do their high school courses, and I'm going to find computer science teachers for them to work with there as well. So we're trying slowly but surely. We're very baby steps right now, but we're trying to get you into the content that you're passionate about, which it would be that computer science classroom. So I don't want that. What we've done in the last couple of years as we're trying to start this, moving forward, we're doing more with computer science classrooms. So I just want to make sure that's known. If you have any questions, we've got this interest form. We can wait around and pick those up from you. And our information is on there. And we'd love to talk to you. We'd love just to, anything you need from us, we'd love to help you with. So.
That's something you can also send, and I'll send it to the students.
Okay.
And they can print it and fill it out.
Fantastic. And we do have an online interest form as well.
Yeah, there you go.
And there is an advisor specifically for Teach Houston, Dr. Shields, and she's awesome. She would love to talk to you as well.
And she's got advice. She's got email on this.
So the University of Houston, thank you guys very, very much.
Thank you so very much.
The University of Houston has a big grant to pull this off. So basically, just to kind of recap, they're looking for people who, once you graduate, if you're not sure you want to go work for industry right away, you think you might want to get some experience describing back what you've done, you can be a teacher for a year. You don't go into a room alone. You're partnered up with a regular instructor, a regular teacher there, because it's considered class for you to get certified to do it if you go into that certification program. So teaching is one of the few professions left that has a pension.
Yes.
You can be a fireman, a policeman, a postal carrier, or a teacher. And in Texas, you work 20 years and you have benefits for life. Yeah, it depends. Yeah, so, right, so it depends. It could have changed over time, but most businesses have no pension whatsoever. They have almost vanished from the face of the earth.
Like, I can retire in 2 years with my pension. Yeah.
And what a lot of people will do is then they start another career.
Yeah, exactly.
So it's like working for the Air Force. That's another area, is the military. So, and the military may be less or more dangerous. I'll let you decide. Depends on the district. And if you speak a second language, that's even more valuable because we're very, very diverse. So the third largest school district in the United States is HISD. So they're enormous, over 300 schools. So it's
1 year required.
The 1 year for certification afterwards is a post-bac program. Yeah, I think so. There's alternative certification programs, but
Well,
I don't know where those stand.
This is an alternative certification program that
Okay.
we've created, part of our grant. And so it is that in the fall of 19, you would take the courses. In the spring of 20, you would do your student teaching. And then that student teaching, you would be in another teacher's classroom. And we gradually give you all the classes, and then we gradually take them away. And then you're done with that semester teaching, 14 weeks, and then after passing all this, there's a test to take for the state, and then you're certified. And after that, you're not required.
Are you certified forever?
You were certified for 5 years, and every 5 years in the state of Texas, you have to renew it. And honestly, it's basically send them a check for $77.
Yeah, well,
that's it.
like a lot of those.
Yeah.
Yeah.
It became a money-making thing. My initial certification was forever, and then after that, I still have to.
Yeah.
Okay, here's the $77.
Got it. Yeah.
So, but I don't believe, and I can clarify this. I don't believe with our full scholarships of this. I don't believe that there's a requirement for teaching a year. But I will confirm that to make sure that's the case.
Yeah, anything you want to send back out, you send to me, we'll get it out to.
I will.
Get
That's
it
a
out
great
to folks.
question. I'll confirm that.
I wished I'd have had this option when I got out.
You know,
because
it's a
I
great-
didn't know what I
no-brainer.
wanted to
For me, it
do
was a
yet.
no-brainer. I was
I had no idea what I wanted to do when I graduated, so it would have
I
been
was
a
like,
chance
I
to.
happened into a program similar to this, and I was like, I don't know, I'll just do something, whatever, you know. And I said, oh, I do kind of like that. And I thought, I'm going to teach. I'll teach for 3 years. If I hate it, I have a degree in mathematics. I can go do something else. And after the first 6 weeks, I went, oh, well, yeah, this is what I was supposed to do with my life.
Yeah,
And
that's neat.
22 years later, I ended up at university. So I'm in my 25th year in education. So, all right. Thank y'all again. Thank you.
Bye, guys. See you. Thank you for your patience, guys, in covering that stuff. So they're trying to spend a bunch of that money on you guys. That's why they're here. They've got enough for, 100 students at a time or something, and they're trying to get a bunch of comp sci because there's a big need for it, and we graduate a ton of people. So we're like, bring money. Yes, come talk to our students about paying for a year to get them off the ground. Okay. And it sounds like we're going to have more info to share with you guys. So that's not a bad way to spend 15 minutes of our time, right? Yeah, started. Exactly. To give money away to students. And they're always hiring teachers, trust me. Okay, we started off this chapter last time, just inching our way into it. To kind of back up a little bit and remind you what the topic is, the problem that we've had with routers is they still kind of do what they did from the very, very beginning, which was at a time when the computers weren't very powerful and everybody had to pitch in money to buy the routers because they weren't in your lab, really. They were handling everyone's data, not just your data. So there was like a little loss of ownership, loss of control. And grant money has always been hard to come by. So if you're now being asked to pitch in some money and give it to a group that's going to run it, you want to spend as little as possible. So routing in the internet has a legacy of sort of least common denominator. What's the least amount of work that I can get these things to do and still pull it off? So lots of options that we could have pursued, we didn't. And all routing on the internet essentially is we look at the destination address that you're trying to get to, and we send it on the best path that we know of. We never know exactly what the whole network looks like. We make a pretty educated guess, and it's good enough, obviously, because it's working. It works. But it has been very evident to us for a long time that we wished we could do a lot more with the infrastructure than that, starting with changing our minds about how and if we want to forward something based not just on the destination address, but how about the source address? Who's sending this? If it's coming from a known hacker, why are we continuing to route it? I used to have conversations with customers all the time about the fact that 50% of the traffic that came down their connection into their router, from their ISP down, was garbage. It was hacking. And they're like, well, if you know that, then why don't you stop it? Why don't you stop it earlier in the cloud? We didn't really have the tools to do that kind of stuff. but we could spot what was going on. We could see the trends and things. So there's been a radical proposal, a departure from the way we've done it, to really step back again and genericize and take another whack at just the overall problem of getting data from point A to point B. And so the idea is to make these devices simply forwarding devices, and we can feed them rules that have lots more options in them than what we can feed a forwarding table today, which again is just the destination address. So here's an example of the kinds of fields that every packet has when it shows up at a router. We can see what switch port it arrived from. If it's implementing a virtual LAN, which means it's a chemical engineer person that's over in another building, but we want it to behave like they're still back there. So when they open their printer list, they see the printers in the chemie building, and when they send out a broadcast, it's broadcast to all the chemie computers. So they may be physically plugged into a switch next to a bunch of computer scientists, but we can't see them and they can't see us. We're really good at implementing that in switches inside of an organization, but we can't do it at all on the internet. You have to build VPN tunnels and do all of this crazy stuff and backhaul everything back to one point and then turn back around. So when I worked at Cisco, if I wanted to send a packet to the printer in Houston, I would have to VPN back to San Jose across the internet. And in San Jose, they would put me back into Cisco. They would assign me a Cisco IP address and authenticate me with my Cisco password. They would take over my machine, basically. So now the only place I can send packets is to Cisco. And now that I'm there, they had to write software to give me away from San Jose to print to a printer in Houston. And I can do it. And it works. We can do it. But you and I should look at that as a network engineer and go, you're what? It's 2 hops away. Why are you going to Timbuktu and back to get that data there? Because it's the only way we know how to do it. We can't get the routers on the internet to add security, to add features, to route based on who I am. And the router at Cisco Houston is not about to let traffic in from the internet. It only lets traffic in from San Jose and Richardson and whoever knows wherever the backup sites are. And so this is a real problem that we have, and for a carrier like AT&T, it's a huge issue. So VLAN ID would be one thing that if I knew what it was and I could write rules based on the VLAN ID, I might route some things differently. Your physical MAC address, what piece of hardware is sending me this? Maybe based on the piece of hardware, maybe that's all I care about. I don't really care where you're trying to get to. If I have a rule that says if it's coming from this computer, send it this route no matter what, then yes, sir, I'll do that. And there's bona fide reasons for doing that. For example, if somebody's hacking you from that MAC address, maybe you want to not forward any of it, regardless of what IP address they're trying to reach. Or maybe if it's a specific type of, maybe it's another router, I send it to a different spot. The type of Ethernet you're using, your source and MAC destination address, the IP source address, the IP protocol that you're running. Are you running for TCP? Is this an HTTP connection? Is it email? Is it time sensitive like voice or video or Skype or WebEx? Maybe I want to treat those packets differently than I do all the rest. Well, you can't do that on the internet. It won't let you. The only thing it will look at is where are you trying to send this packet. That's it. So out of all these things, the only one we look at today is this one right here. That's it. And there's tons of other stuff that you could look at as well. So we want to make this more generic and basically say we would like to come up with not forwarding entries for a destination-based forwarding table. We would like to come up with something more generic, a rule that says if you match certain fields, if you match, we can put things into one or more of these fields that you could match, then here's the action we want to take. So when a packet comes in, quickly decide if it matches this rule by looking at the pattern. So if I put something in Ethernet type, then see if it matches that. If I don't, then it doesn't matter. So figure out what you can. If it matches, take these actions. And if there's any statistics that you need to update, then I want you to do that as well. So that's the container. And one of the packages, one of the standard proposals that lots of people have adopted is one called OpenFlow. And so we consider these things to be flows of data now. So here's some examples. One of the things that's a little surprising to people at first is just by doing this, you can actually replace lots of equipment that's on the internet. So for example, if I just want this to be a regular router, then I can ignore all the fields except this one. And I might have an entry that looks exactly like what I have on a router today that says, if you're trying to reach this network, then send it out port 6. That's exactly what we would have in a forwarding table today in every router on Earth. If you basically want to say, if you're trying to get to TCP port 22, then drop the packet, that's something that only a firewall knows how to do. You can buy firewall code and have your router run that as well. You can sometimes buy firewall cards, hardware accelerators, but buy, right? These are separate functions from routing, and so you pay more. People sell firewalls. And so firewall rules are based on other patterns. Here's another one that says, if it's coming from this person, this IP address, drop it. Their machine's been compromised. We saw them sending these virus messages. It's been hijacked to be a robot in a denial of service attack. Don't forward any more packets from that device. You can do something like that. So I've been able to teach these flow rules to a generic forwarding device, and it can now do all of these things. If I want this device just to act like a switch, just a regular old switch, I can just say, you know, if it's coming from this hardware address, then send it out port 3. That's something that maybe just a switch would do. So if I can push the cost down of these devices and get them mass produced so they're the same for everyone, regardless of whose name is on the front. Maybe Cisco buys them and resells them for next to nothing, and then what you're really paying Cisco for is all of their algorithms that decide which rules each device needs to have and how they manage it. And if you sign up for security services, for example, something that, for example, learns new threats as they appear around the internet and automatically push new rules into your corporation's routers so that those packets, if any of them haven't made it already, they won't, and you never have to lift a finger, that's a subscription-based service. Please feed me new rules during the day to keep me safe. Like, that's something that you would want a device like this to do. So it has the ability to change kind of how we pay for these things as well. So it's got some abstractions. We talked about network address translation. And so one of the things this can do is to see if it's coming from this IP address range and it's trying to go to this IP address range, then change it. You can implement lots and lots of stuff this way. So here's an open flow example. There's a controller, which is basically a server that's running code that talks to these routers, because these routers aren't making these decisions on their own anymore. These routers aren't keeping in touch with other routers in the neighborhood. Hey, who do you know how to go see? What networks have you discovered? Instead, what these routers are doing is feeding all the information upstairs to this controller. And the controller is running algorithms that then make a decision based on a broader set of knowledge, what rules should be downloaded to each of these devices. So you could have one that says if it's coming from 10.3 and going to 10.2, then send it out over port 3. So it'll go that way. Here's one that says if it's coming from 3 going to 2 and it came in on port 1, send it out port 4. And here's one that says if it came in port 2 and it's going to 3, send it out port 3. If it came in port 2 going out 4. So these are not hard for us to look at as computer scientists and imagine writing code that can implement this. This is not very complicated. And so it turns out to be extraordinarily powerful. So how do you build these forwarding tables? Where do these routers get these things from? It's from the next chapter. So what this chapter basically talked about very briefly was IP and fragmentation and NAT and V6, and then at the very, very end, we ended up talking to you about the part that would be left behind in the router if you were to migrate your network to an SDN type architecture. So again, this idea of changing these approaches, genericizing your forwarding table, coming up with these rules with open flow or some other kind of construct that's called software-defined networking, SDN. That's the overall name of this field. And that's what this last section of Chapter 4 dealt with. All right, so we're not going to miss a beat. We'll just plow right on ahead into Chapter 5, which is the network layer control plane. So this is brand new. And what we've done now is taken all this software that was making these decisions that resulted in the construction of a forwarding table, and we're removing it from the router. So it still needs a forwarding table, but now we're going to take on that responsibility ourselves in the data center. So now we're like mission control. So instead of, it's kind of interesting, we're kind of going the opposite the way some fields are, where we're trying to sort of make devices in the field more intelligent about how to make their own decisions and not have to have a connection back to some like the mothership and all that. We're going exactly in the opposite direction with this. We're trying to get the routers to stop making those decisions themselves, send all of the telemetry data. This link has gone up, this link's gone down, here's how full my buffer is, this one looks like it's struggling, I've discovered a new network, etc. Send all that upstairs and somebody else will make a decision how to do it. So we can build cheaper devices at the edge and put our money into making them really fast instead of building a whole server, which is what a router basically is. It's just a complete Unix-based server system with a bunch of specialized hardware. So where is this decision-making going to get done? It's going to be made in the control plane. So what this chapter is basically going to introduce us to are some of those concepts, some of those terms. So there are routing protocols that people are very wed to, that they like, that they've run typically for years, that produce these forwarding tables. Things like Open Shortest Path First, or as it's known, OSPF, or another one, Border Gateway Protocol, or BGP. That's the one that all the routers on the internet run. That's how they share information. Now we're going to see things like OpenFlow and ODL and ONOS controllers, Network Operating System controllers. OpenFlow is something we'd all use. ONOS is something a carrier would use, like Telmex or France Telecom or Pacific Bell or Bell Canada, somebody like that. And then we'll see how things like ICMP and SNMP can now fit into this plane a little bit here. So remember, the abstraction is there's two parts to what a router does. It forwards, which is actually the part of moving the atoms, in our case the bits, but I like to talk about it like it's physical, physically forwarding the envelope from one mailbox to the other. So that's one thing that happens. That's forwarding. Of course, it's all just data. And then the routing is making the decisions about how you're going to do. So this is the travel agent who plans your trip. This is you once the trip starts. And the first thing you got to do is get in an Uber, and then get on a plane, and then take a train, and then take a ferry boat, and on and on and on. All right, so the routing is the one that decided that's the route you should take. And the person right behind you might be told to do it a different way. Especially this morning, when most of the airlines had some issues. Do you guys know what the problem was, by the way? It wasn't the network. That should be your gut reaction always. Come on, guys. It wasn't the network. No matter, even if you know it was. Your first answer should always be, don't try blaming it on the network again. You guys write crappy code. That's the problem. So you got the best defense is a good offense. What if you're responsible for both? You're screwed. Yeah, I used to know one of those guys, God rest his soul. So yeah, so the network did not go down. What happened this morning is there's a system that everybody uses in the industry to calculate the amount of fuel that you need based on the load of your plane, so you can get certified, and if you don't get the certification from them, you can't take off. So that went down, probably their network went down, and so nobody could take planes off. Yeah, it was crazy. I think Southwest was like totally grounded, believe it or not. And then for people like Delta, it was just their smaller planes. All right, so two approaches to doing this control plane, if you will. What we've always done is done it in every single router. What we're trying to do now is do it in the cloud with software-defined networking. So again, the per router control plane, we did this stuff in every single router. We still have this logical division. It's kind of interesting because these forwarding tables are so dependent upon that we have gotten to the point where we don't even have time to go and ask the routing program to tell us what's in its table. It has to produce the table, and we have to store a copy of it in this crazy ternary content addressable memory in every single line card. So there's like a 1,000,000 line routing table possibly in every single one of your 180 input ports. It's crazy to make it that fast. That part's not going to change, but what's going to change is where the rest of this stuff runs. So the idea is that we'll logically centralize it And all of this stuff in the top half of this diagram is being done in like an Amazon web server data center or some Google data center or something, something like that. I mean, what could go wrong? Come on, obviously. So we now need to spend some time, now that we kind of got that concept out of the way, taking a look at the algorithms that get used. This, we think, isn't going to change based on where you choose to run the program that implements the algorithm. So we're going to take a look at the algorithms that we use to calculate these forwarding tables. And they fall into two basic general categories. One of them is link state, and the other one is one based on Dijkstra's algorithms, one based on Bellman forward algorithm. And we'll take a look at both of those. So the idea behind a routing protocol is, based on what you know about who you can see, try to come up with a pretty good recommendation on where I should go next. So this is like asking the guy at the gas station at the country road where there's like 4 ways you can go. And, like, well, I heard there was an accident up the road. Well, I haven't heard about that, but, it's possible. You could take this one over here, but, after dark, there's no street lights on this one. The state didn't put them up. But over here, it's going to rain. So I think I would go this way if I were you. And that way, if you guys get tired of going, there's a couple of hotels along the way. Say hi to my sister-in-law if you stop at the first one. It's like, how confident are you that's the best path? In my head, I'm hearing like, down, 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 like, the show? So Deliverance with dueling banjos. So, but what it hopefully is a good path, good enough to kind of get you to the destination. So that's all routing protocols are going to promise you. They never promise the best path. Inside of an institution, like the University of Houston or like Xerox Corporation or like American Airlines or something like that, then yes, you can have something that talks to every other router inside the organization. Even that's rare if you're big. So those are better, and maybe those are best. But as a router manager, how do you define what the best path is? Is it the one that's going to get the packet there the fastest? Is it the one that's going to disrupt the fewest delay-sensitive packets along the way? Like, in other words, is the best path the one that slows you down as necessary to keep delay-sensitive traffic prioritized? Is it the one that's going to cost you the least amount of money? Maybe one of these links you pay for. Maybe one of them like a satellite link and you get charged by the minute. Maybe one of them adds up the amount of bandwidth that you send. Is it the one whose destination router has the least full buffer for the next hop and therefore the least chance of having to drop a packet and retransmit it? Now, how do you want to measure what best means? You get to pick that out, and these routing protocols give you the ability to set some of those variables and decide. You also can come in like the hand of God and say, thou shalt forward on this path, and that's it. That's the end of it. So one of the big weaknesses, another weakness with basic routing tables is once they make up their mind, they're stubborn. So if I have 5 paths to get from point A to point B, and this one's 50 megabits per second, this one's 50 megabits, and so is this third one. And they all have a way, I'm not going to draw a bunch more routers, but they all have a way of getting to your destination here. What routing protocols do is they pick one. Let's go this way. All packets will go that way. That's great unless you have more than 50 megabits per second worth of data to send. And, you and I are like, well, why can't you send some of it this way and some of it that way? And it's like, what? How would you do that? We don't do that. We pick a winner and we stick to it. So you might send some stuff this way, but you're only going to pick one at a time. It's destination-based forwarding. The answer is you're not going to change the routing table every packet. There's just no concept of doing this in the original way these routing protocols were written. So inside of an institution, people implement lots of extra rules, but you can't do it at the core. You can't do it on the internet. So this is a big issue, and it causes people to just buy giant pipes that are big enough, so big that they're bigger than any single stream could ever want. So you're never going to get burned by the fact that you can't divide the traffic up. In the telephone network, we've done this traffic shaping, as it's called, from the very, very beginning. From day one, we optimally used every single link that we ever had. there may be a capacity for 1,000 total simultaneous phone calls from Los Angeles to New York. 40 of them through Omaha, 60 through Tulsa, 180 through El Paso, so many through Denver, Des Moines, on and on and on. So you have route diversity to do that, but there's never going to be a link that can handle all 1,000 of them. Why would you build a network to do that? Do you build one highway for everyone to get from Los Angeles to New York? Or do you let them just kind of go like this? So this doesn't even make engineering sense, but that's the way it runs. That's the way the backbone core protocols were designed to run on the internet. So people, you know, they've had enough of this. After 40 years of this stuff, it's like, enough. We need to do this a different way. So what you find are some of the big providers like Verizon or Level 3 or Hurricane Electric or AT&T or some of these, they do this stuff inside their own network, but they just can't do it with anyone else. They can't figure out how to pull this off. So we're overdue for, I don't know if I want to say that, I guess I could. We're overdue for an NMF on the internet protocols. And that's what we used to call it. That's the way we used to refer to this thing, is like when you were ready to like get that routing protocol out of there and put something else in, that was like the big insult for your network. So it was a pretty good insult, I must hand it. Revolution, maybe, I don't know, but network people are different. They use different phrases than the rest of the society does. So I apologize if that offended anyone. I mean, it's how could it offend someone? So routing protocols, their goal is just to give you something good. So again, how do you decide what's the best? So we need to come up with a way of abstracting what a network looks like so that we can feed it as a data structure into our algorithm. Regardless of what the algorithm is, the first thing you need to be able to figure out is, how are you going to tell me where the nodes are, and how are you going to tell me where the links are? And if there is some sort of a cost that we want to assign to each of these links, how are you going to do that? So that's what this diagram is trying to show, and I'm sorry the numbers are white instead of black. Can you still see them though? Okay. So I can see 6 routers and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different links. And I'm going to define the links as pairs in a linked list that show the source and destination. So every link connects one thing to another. That's because they buy my technology to do it, those private line point-to-point circuits that I keep talking about. Everything is still connected with those same technologies, copper and glass. Which one do you want, right? So those are the rules, and if you dig down enough, everything's going to be a pair of connectors. Never 3, never more than that. So this abstraction is kind of useful for us. And now we can start writing algorithms to calculate the cost. So let's suppose one of the things we want our algorithm to do, we want to write one that calculates the least cost path between 2 different points. And we'll see some variety of ways of pulling that off. But we need some nomenclature if we're going to keep track of cost. So the nomenclature is going to be C and then the pair of items, and we'll give it a numerical value in this case. So the cost between W and Z, the least cost is 5. Or at least the cost of this link between W and Z is 5. Is that the best way to take to get from W to Z, by the way? No, it isn't. So we can see that going down to Y and then across is 3. It's less. I don't know if that's time or money or, you know, who knows what. Percentage busy. Maybe these things change constantly, probably. But for now, we'll just look at a static diagram. So the key question, if we're going to build an algorithm, is how do we figure out what the best way is to go? And your algorithm is going to find that path, and it's going to write it down as a rule that goes into your forwarding table. And it's going to be given to every input card on your router to say, heads up, if you get something at this router that's headed to Z, send it over the WZ link, which might be a specific port number. So I cannot stress enough, the goal of the routing table, it must produce a forwarding table. That's its goal. It has to produce the forwarding table, or the switch fabric doesn't know what to do with the packets. That, whatever the algorithm is, that's the ultimate goal. You can hard code one in and sit down in front of a text editor and do it that way. That's fine. You can edit the ones. You can hard code some things in. Most managers will. All right, so how do we want our routing algorithm to work? Should it take a global view of things? Can it? It can't on the internet. Do you want it to be decentralized where each router has the ability to calculate on its own? Do you want it to be relatively static where it ignores changes that happen and still send people, that way? Or do you want it to be super dynamic where the instant something happens, it will update the routing table? Phone calls, that network updates instantly. If there's a loss of a link, the phone call stops. And it may get rerouted. One of the goals of the 5 ESS switch was to reroute calls without having to disconnect them around congestion, around problems, around cable cuts. And so that's an example of where you want that information instantly. On the internet, you usually don't because things are spurious. Just because you can't send a packet may mean that there's a really serious problem with the circuit underneath. It may mean that it's only going to last for 1 second. And so aren't you glad you didn't run and send everybody home? This is sort of like, what do you do when the projector bulb burns out in class? This is like my nightmare. Do we cancel a lecture? Well, I have options. I have WebEx. Is there a spare one built into the projector? Some of them have it. If I call the number on the thing, are they going to come over quickly to do it? So you got to make a rule, and that turns out to be kind of a challenging problem to solve, is how do you deal with bad news when a route kind of goes down? So we've got to make all those kinds of decisions. So link state and distance vector are the two classes of algorithms that we'll learn. Dijkstra's algorithm, have you guys heard of Dijkstra's algorithm before? So it depends on your background. I think people that had more math may have, it seems to be like half and half. What Dijkstra's algorithm depends on is that everyone knows the cost to get to every other node. So this is going to be a protocol that you will embed in an algorithm or a routing program that you run inside of a company, where you can, it's possible to actually talk to every other router. It's not on the internet, so this won't work there. The key giveaway is this last bullet. All nodes have the same info. It doesn't mean they have the same routing table, forwarding table. It just means they're all aware of who everybody else can see and at what cost. They all know that. It takes time for this to propagate through the network, because to keep from flooding everything, what you'll do is sort of send to your neighbors what you know on the other side. And then while that's going on, you are receiving data from your neighbors about who they can see. And so you pass that along. And then the next cycle, you're receiving data about who their neighbors can see, and so forth. So it takes a while to propagate through, but with that data, you can compute the least cost path to every node. And you produce, of course, a forwarding table. That is your goal, is to produce that. And after k iterations, you know the least cost path to k distances of destinations. So we use this notation of cost, of the distance to a specific destination. It may be directly connected to us or not. The node that is immediately before that destination that we've been able to get to so far, and then we work our way through this algorithm and we whittle down what we don't know. So it's best shown with an example. It's kind of a fun algorithm to work through. So here's the way my code would look. I'm going to basically set the list of things I still have to do to everything by writing down that the list of the ones that I've done is my first node. I know how to get to myself. So I start off with the here's what I know so far list is just me. I know how to get to me. So if somebody sends me a packet from my LAN and it's for another LAN that's attached directly to me, I already know how to do that. And then for all the remaining nodes that are left, all the remaining routers, nodes are routers, one by one by one, I'll pick the ones that are adjacent to me and calculate the cost to get to each one of those things. And if I cannot see that router directly, then of course it costs infinity. So that's our startup. So if I go back to my diagram up here, just to make this sane, and I'm starting off with router U, that's our book's favorite, it always likes to start with U. I know how to get to X, V, and W. Agreed? And that's it. Everybody else, I've heard there's this magical router Y and Z, but they're in infinite cost to me. I have no way to get to them. But I do know the cost to get to these three. So that's where I'm going to start with. And then at every iteration through my algorithm, I'm going to pick a router and ask it who he knows how to get to and update my costs if with anything lower. So I'll show you what it looks like. And you can go back if you like reading the code. The code's actually not hard to understand. But I have to kind of kneel here because I got to write in a little bit of detail. And I'm going to take some pictures of this stuff as well to show you what's going on. Now, what irritates me right off the bat is they immediately switch the, yeah, you notice that too? Yeah, it's not the same network diagram. Thank you very little. So, all right, so here it is. So the idea is that from you, I know how to get to V. I want to change to a different pen, especially before I get sick to my stomach from that horrible color that I chose. The cost to get to router V is by going through V, and of course, because that's the one hop away, and it'll cost me 7 units to get there. And I will go, the last step I'll go through is U. So this sounds sort of redundant, but as we get further into here, sticking with this nomenclature will work. Do I know how to get to W? Yes, I do. How much is it going to cost me? It's going to cost me 3. And who can get me there? You can get me there. And it's true, you can. How can I get to X? I can get there directly in a cost of 5 by asking you for help. That's yourself. Can I get to Y or Z? I have no idea. They cost me infinity. So I'll advance a slide. Don't want to use that one. Let's do it here. And out of the choices that I have, the way this algorithm chooses to do things is by picking the least of them. Now, they're all going in different places, so it's a little bit arbitrary, it may seem, but you know, I can get to V in 7, W in 3, and X in 5. Therefore, that makes W the winner. What? Yes, you pick the one that's got the lowest cost. If there's more than one, randomly pick one. And my request to you, please, is if you're doing a homework or a problem, and there are 2 possible routers you can pick the one on the left so that it will match my answer for the TA. And you won't have to argue with them about, like, it's the same if I pick the one on the right. Yes, but then you're likely to have a meeting with them over it. So I'm going to pick 3, and what this means is I'm confident that I know the least cost to get to W. Because any other path I choose that could also possibly end up at W is already more than the one that I have. So it's never going to beat this one. So the path that I have to W, I have confidence it can never be less. Do you see that? You want me to repeat that? So I choose to conclude after this first round that I must have the best possible path to W. Because even though this network is a spaghetti bowl and there may be lots of other ways that I'm going to discover later how to get to W, they're going to all begin with either this link, or this link, because those are the only 3 things I'm plugged into. And the other 2 already are higher than the one that I'm choosing. So how could they ever go down? You're going to start with 5 and start with 7. You're only going to add to it from there. So therefore, I have confidence that I have discovered the least cost path to W. And I will circle it and write it down, and I will add W to my list of routers that I'm confident that I've solved. So it goes from N prime, goes from U to U and W. And so now I go back and I ask, now that I'm confident I know how to get to W, let's go ask him what it costs him to get to various things. Hey, W, who do you know how to reach? W comes back and says, I know how to get to U, X, V, and Y. Agreed? So one by one, we go and look. What do you cost to get to V? Let's see. W knows how to get there in 3. And I already know that I know how to get to W in 3. Therefore, the total to get to V is to 6. And I get there by handing it to W. All right. I'm already done with this one. I circled it, so we're finished. For X, was he able to improve my situation to X? How long does it take you to get to X? It takes you 4. And then how long does it take me to get to U? 3. So that's a total of 7. We're no better off. Let's keep for now that our belief as the way to get to X is in cost of 5 to go through U. Well, in other words, directly from ourselves. What about Y? Yes, I do know how to get to Y. Fantastic. I no longer have to write it down as infinite. What is your cost to get to Y? It's 8. And my cost to get to U is 3, right? So I can get to Y in 11 by going through W. Z, still unreachable. Out of these, the one with the least cost is the one to X. So I'm confident I now know the least cost to get to X because the other ways I have of getting there cost more. All right, so that's kind of the idea. So I'm going to add X to my done list, and I'll do this again. This time I've discovered a path to Z. How? Because I've decided I've got the least path to X, I'm going to go and ask X, hey X, who do you know how to get to? X says I know how to get to U. Don't care, I already know that. Know how to get to W. I've already been there too. Finished with him. I know how to get to Y. Oh, how much do you cost to get to Y? I need 7 to get to Y. And how much does it cost to get to U? I decided here in this red circle that it would cost me 5 to get to X. I don't care how. I just know the cost was 5. Therefore, your 7 plus that 5 gives me 12. So I'm better off sticking with the 11 that I already had. So once you know the cost of the new link, you don't look and eyeball the diagram and try to guess the least cost. You go back to your table and you look at what answer you wrote down. And so what about, can Y get me to Z? Yes, he can get me to Z in 2. And what did it cost me to get to Y? You know, it cost me 11 to get to Y, so 12, 13. I did this wrong, though. I got to figure out my least cost. I think I figured out was going to be less. We haven't finished Y. We asked X. That's who we asked. Yeah, that's why. I'm still on this one. So I asked X, who do you know how to get to? I'm not quite to Y yet. X knows how to get there in 9. We'll change it later. But for now, we have 9. How much does it cost me to get to X? 5. 9 plus 5 is 14. So for now, my best path to get to Z is at cost of 14 by going to X. Well, he's my only way of getting to Z. So obviously, he's the best way to get there. All right, a couple of more. I chose 6 from this round. I was able to improve one of my links, but not the other. The one I was able to improve was the cost to get to Y. And I added U, W, X, and V. So V is the new guy. Here he is. He knows how to get to Y in 4. What does it cost me to get to him? I can get there in a total of 10 now by going through W, or in this case, going through V. So I'll update it and get it there. So step by step. I have a feeling I'm kind of going too fast, but you guys can go through the algorithm. And what you're going to see at the end is that you've chosen only the links in red. You have a network that has 10 different links, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 links, and you're never, ever going to send a single packet over 5 of them until the link costs change. Somebody else might use them. You will not. So if X changes his mind about how to get to Y, he'll advertise a new number. Maybe the links you use will change. But this is typical. You will only use a subset of the links. You can draw a tree from this. It is a tree, but you can draw one that eliminates all of the other links. So what you'll find if you draw a tree from this is that it's kind of inefficient. Is it going to cooperate? No, because I didn't move it correctly before. So my tree starts at U, and it goes, I have 2 paths. One of them goes to X, and the other one goes to W, correct? And then W goes to V, and then V goes to Y, and Y goes to Z. I can tell you right now I don't like this tree because the one on the right, Z, is very prone to network outages. He's got to go through a lot of hops to get back to you, but that's my lowest cost. So it doesn't maybe look like that when you take a glance at the diagram, but That's the way we did it, and that's how Dijkstra's algorithm works. Here's another example. What they didn't do in this one was like circle the numbers, but you basically can see in the first row, the path to X was the one that I had the most confidence in. It was this path here, so I decided we would settle for that. So I added X to the list of ones that I'm finished with. The next one, I had a choice. I could have picked the path to V or the path to Y. I chose the path to Y. You could have picked whatever you wanted, and you just basically, one by one, you go down until you've listed all the routers. Yeah, but he didn't. Yeah, they didn't. I would like for you to, that's all. So you're not going to get it wrong, but you may have a debate with your TA. That's all. Like here, you had a choice of 2 routers that were the same cost. Which one are you going to decide you are confident that you know the least cost of, add it to your finish list, and go ask who he can get to? I would in the table. Yeah, look at the one on the table. No big giant deal. So here's the tree that resulted from that. I just drew an example of that for you. Some of these links you never end up using. Okay, so with Dijkstra's algorithm, you have some interesting artifacts with this. With N nodes, you're going to have to check all of them. So it's basically an order N squared algorithm. You have to check everybody W that's not an N, and so you're going to be doing N times N plus 1 over 2 comparisons. There are more efficient implementations of this algorithm that this book does not cover that get it down to N log N, which is a lot better, but it's still expensive. The other thing worth noting here is that oscillations are possible. So here's initially a table on the bottom left. It showed that D knows how to get to A in 1, and B knows how to get to A in 1 plus E, and C knows how to get to A by going through B with E. So this is 0 cost initially, so of course these guys are going to go crazy, you know, on this kind of stuff. So what happens if the costs start to go up? What will happen is people will find new routes. D still has the same route to A that he had before, but B, now that he's faced with a 1 in this direction and a 1 plus A, he's going to start sending his traffic now this way instead. And so what can end up happening in real life, and it's a terrible example, and I'm sorry, but it's the one that they did. What can happen, as you can see, is you start flipping back and forth and back and forth. So oscillations are a problem. It's particularly a problem if links are going down and you overreact to it. So we have this concept called good news travels fast, bad news travels slowly. And that will tampen down some of the oscillations. If you learn about a new network that comes online, absolutely immediately start using that link. But if a cost of a link goes from 1 to 100 because its buffer got really full and stuff, give it a chance to fix it. Don't go from 1 to 100. Tell everybody, you know, it's gone up. I'm going to say we're going to go with 2. Still 100. We're going to go to 3. It sounds like some old joke, like the cat died, but you don't have the heart to tell someone, one of those kind of deals. Okay, that's one class of algorithm. The other class, the major class of algorithm, is a distance vector algorithm. So what we just looked at was link state based on Dijkstra that you will run inside of an organization. The distance vector algorithm is one that uses a concept from dynamic programming, an algorithm popularized by the Bellman-Ford equation. So what this one basically says is, of the stuff that you know, pick the one that's the least cost. And the way you're going to do that is by picking the least cost that you know to get from X to one of your neighbors, and then trust him to tell you what the cost is from there. Do not try to go and calculate it yourself. Let him tell you what his cost is to get to Y. And if the combination that you can calculate to get to him and that he can take to get to the destination wins, then that's the one you go with. So you're prone to being lied to. You're prone to having bad information sent to you. You're prone to having bad route costs injected into your stream and believe them. So there's a source of hacking possible, but basically the idea is your computational load is much, much less. So this takes a while for the data to kind of propagate its way through the network, which we mentioned. All right, so here's my same network. If you'll grant me, give me a mulligan here, obviously you can see that the cost to get to Z through V from U is 5. Let's see, do you see the path? It looks like to get from V to Z is 5. Down, over, and up, right? Okay. And the cost to get from X to Z, which sounds like ecstasy. There's a lot of funny sounding things in this chapter, I remember. From X to Z is 3. And the cost to get from W to Z is also 3. Well, 1 to 2. Forget straight from X to Z and W to Z and V to Z. You think this one should be 4 that's highlighted? Whoops. To get from V to Z, it is 5, right? Okay, so why did I pick V and X and W? Because those are the ones that you can see directly. So I'm basically cheating and saying, let's suppose we've already done all the work to figure out the cost it takes our neighbors to get to Z. Now that they can tell us what they need to get to Z, what's it going to take us to get to Z? Well, it's going to take us adding our own cost to get to this neighbor and then tack on what they need. So for me to get from U to Z through V, it's going to cost me 2 more. That's my least cost path. It could have been this way, but it isn't. It's this way. So 2 plus 5, they told us that, so we'll just trust them on that. And then what's the next router that I have nearby me? I have X. It cost me 1 to get to X, and what did X tell us they needed? They needed 3 more. So we'll write that down as a pair, and that's going to be the one that wins because it takes me 5. Either way I take, I can go here, I can go there, but I have a direct path. I got to do that first to get to W, and so that one's going to end up being too expensive. So 4 it is. 4 is going to win. So I'm going to write down in my forwarding table that my path to get to Z is via X. So if I get a packet that needs to go to Z, send it out whatever port the cable runs that goes to X that I bought from the phone company. That's how we crank out these routing tables. There's a different way of drawing the data structure for this, which PowerPoint does not want to show me. I ate my vegetables as a kid. I did everything right. I never missed a day of school. Okay, there we go. Distance vector algorithm. So you'll basically run through this thing and try to calculate. So at the beginning, your neighbors may not know the cost to Z. It may take them a while to learn. So if I go back up to the diagram, and you'll see why. The first people that are going to learn how to get to Z are the people with connections to Z, W, and Y. In the second round, the people that are going to learn how to get to Z are the people that have connections to them, U, V, and X. And then if you have more complexity in your route, it's going to take more and more rounds to get it done. But you never have to go and talk to Z yourself. You never have to go and talk to W and X. You just keep up with your neighbors, which happens to include W. All right, so the idea here is from time to time, you're going to advertise what you know, maybe every 30 seconds, to your neighbors and say, hey, here's what I know. Maybe you just send me changes, but you will need to take on the responsibility of letting your neighbors know what's going on. And when your neighbor receives this new estimate, they're going to update their table as needed. Most of the time, nothing changes, but sometimes it will. So a routing table may learn about lots and lots of things out there. It may throw some of them out if it's not ever sending routes to those networks. So you will prune this thing to get rid of things that you don't really care about. So this will converge. It can be proven to converge. So the data structure, the graphic that they used to go with this is this one. 3 routers on the left, X, Y, and Z, and they each have a matrix. When you first start out, all they know how to get to are the people to whom they are directly connected. which is y and z. It's this network over here on the right. So x knows how to get to itself in 0, x knows how to get to y in 2, and it knows how to get to z in 7. We can see that if this is going to work, it's going to figure out this path instead, right? Because this one's less. So what does y know? Y knows the same kind of stuff. What does z know? So they've learned these three things, and so they're going to send what they've just learned, what they've just changed in their table, which includes themselves, to their neighbors. So x is going to send his row to y and z. Y is going to send his row to x and z is going to send his row out as well. So let's just focus on the top one up here. I'm going to learn from y the line that he gave me. I'm going to learn from z the line that he gave me. And how is that going to change how I choose to get from x to y now? So what I can look at is figure out who knows how to get there, and I'll run this Bellman-Ford algorithm for each one of these. To get from x to y, I'm going to calculate, I have two different ways to go. I have y and z. So I'll first figure out what it takes me to get to y plus what y tells me is his cost to himself, and then I will calculate the cost to get to z plus what z tells me is the cost to get to y, because I'm trying to figure out this first question mark, which is what's my least cost to get to y. So let's plug some numbers in and figure that out. So the cost it takes me to get to y, I believe, was 2 before, correct? And that fills in this number here. Y doesn't need anything more, so that's 2 plus 0. Okay, that's one option. The other option is to go the other way. What does it cost me to go to z? I believe it costs me 7. And what does z need to get to y? He needs 1 more. That's 8. So the one that I had wins. I don't change it. It was 2 before. It's still 2 now. Okay, what about the other question mark? This is the concerns getting from x to z. I thought it was 7 before. So what are my two choices to get to z? I can go directly to z, or I can go through y. What do those two look like? To go through y, I'm going to take my cost to get to y, which is just updated. It's 2. I just figured that out. Let me undo this stuff. I thought that wasn't there before. Well, I just need to make sure not to save it. Okay, so it's going to cost me 2 to get to y. And then what does y advertise that it takes to get to z? Well, let's look. It's here in the table. Y says he takes 1 to get to z. So that's one of my choices, 2 plus 1. The other option I have to get to z is to go directly to z, which is the cost from x to z, which I believe was 7. And then to get from z to itself, which he tells me he can do in 0. So that's 7 plus 0. My winner is 3. So I was able to change my table and go from 0 to 7 to 0 to 3. That now counts as an update, which I then have to advertise out to the other guys again. And you just keep going and going and going. This one's much harder to do on an exam, so I seriously doubt you'll see it after the homework. But Dijkstra's algorithm, you absolutely will want practice. And so I will show you on our animation site. It must be this one. If I were king, I would put all of these on the same page. Okay. Dijkstra's and Bellman-Ford. So here's Dijkstra's algorithm. Can we draw a table for this one? You want to do this and then we leave? Or do you just want to leave? Yeah, okay. I'm on to you, clowns. I'm on to you. Not going to work. All right, let's see if we can do this. Well, of course, I mean, let's see if I can do it. Yeah. Yeah, which is, you guys, this is your free entertainment of the evening, because the chances are very good that I cannot. Yeah, whatever. Don't throw me a bone. I don't deserve it. All right, so we're going to start off with you. I got to turn this off. We're going to start off with you, and let me make sure I'm using exactly the same format that they did in the PowerPoint so I don't confuse you guys, because I learned a different way to do this originally. They're going to do skip numbers. Okay. So I'm going to have M prime over here, and I'll start off with U. Who do I know how to get to? Well, U, V, W, X, Y, and Z. All right, thank God it's alphabetical. Can I get to V? Yes, in 1 by going through myself. Can I get to W? Yes, in 2 by going through myself. Can I get to X? Yes, in 6 by going through myself. What about Y? No. What about Z? No. Which one of these is the winner? This is the winner. So I'm going to add U and V. I'm going to add V to my list, and I'm going to ask V the same questions. Does V know how to get to W? Yes, he does. What does it cost him to get to W? And what does it cost me to get to V? So that's a total of 6. That's not any better than I had before. Stay with what I had. Can V reach X? In 5, correct? That's 6. That's no different than what I had before. I will leave it alone. What about Y? Can V get to Y? Directly? No. Can he get to Z directly? No. Who's the winner? 2. So I could have added both of these at once if my algorithm were a little smarter. All right, what do I know now? Who does W. Who does W know how to get to? Does W know how to get to X? He takes 5, right? And what does it cost me to get to W? No. Right here, look in your table. Don't eyeball it on the diagram. Use your table. That's the trick. That's the only trick in this exercise. That's it right there. You just hit it just to go back and look at the table. The rest of this stuff is no-brainer, but that's where you'll get tripped up. That's the only place I think you'll ever get tripped up, once you learn the basic mechanics. So I know how to get to X from my new guy here, W, in 5, plus the 2, I'm no better off, correct? So the cost was 7. You were right about that. Can I get to Y? I know how to get there in 9. What does it cost me to get to W? 2, so it's 11 through W. And what about Z? Yes, 7 plus the 2, 9 through W. I like this one because it's winning left to right, which is kind of interesting. So I now have U, V, W, and X. I can mark off the list because I just circled him. Does X know how to get to Y? Yes, in 9. And what does it cost me to get to X? 6. So I'm stay the same. And does X know how to get to Z? No. So thanks a lot, X. You screwed up my perfect pattern here. U, V, W, X, and Z. The last guy I have is Y. Does Z know how to get to Y? In 6. What does it cost me to get to Z? 9. That's no better than what I had, correct? So here's my final state. If I draw the tree out for you, the tree, and let's color it in first because that makes it a little easier. I've chosen to use a path from U to V. The next red circle was from U to W through V. And then I know how to get to X through U. And I decided I knew how to get to Y through W. And I know how to get to Z through W. So those are the ones that I highlighted in. And my tree is U, X, V, W, Y, and Z. Agreed? Yeah, why did I not have, I should have that one lower, shouldn't I? Yeah. Yep, you're right. Like this, right? Thank you. Happy now? I told you I'd screw it up. It's on the very last freaking arrow. It's so close. Yeah, all right. So that's how you would draw the tree of what you're going to use. So do you see the inherent inefficiency in this? If I showed you this diagram and said, give me as much traffic as you can to Z, you'd use every road possible. It's an evacuation. You know, you want to get traffic over there. And you're okay if they have different costs. If it means delay, then you should deal with the fact that they're going to show up at different times. But we just did that in TCP. It can deal with that. It can handle putting them back together in the right order again. So this is one of the big motivators for SDN. You want to be able to say, just pick some people to go left and some people to go right and use them both. I paid for this network. Do not leave it empty. That's kind of the challenge. All right, guys. Thank you very much. That's what we have. See you on Wednesday online. Is this all new to all you guys? Could you write the code to do this? Yes, you could. Yeah, not hard. Nuances will kill you, but the basic stuff is doable. All right, thank you very much. And for your patience again at the beginning, thank you. I have a feeling some of you will actually go for that. It's a good, it's a guaranteed end. It's a guaranteed job, and you'll be a student the first year, which means I think you get paid $10,000 or something, but they pay your tuition, and then after that you're certified, and you'll get hired like that immediately. And then you have 19 years left, and then 18 years left. I could still work 20 years and still have a pension or something. You know, it's kind of crazy.